Hello, potential energy diagrams. Let's draw them and label them. Tracking process of a chemical reaction requires you to know some vocabulary related to certain sections. So, sure. First thing, draw this as best you can. So pause.
Yes. So here's the important thing you got to draw. Ready? Notice that the reactant side on the left is higher than the product side on the right.
Mm-hmm.
So that's really the key piece here.
Exothermic.
That this starts high and finishes low.
Mm-hmm.
That's the key. That's how I know it is exothermic. And that's review.
Yeah. Next one.
Endothermic.
Pause it and draw.
Opposite.
Opposite of exothermic.
Yeah.
Energy of the product side is higher than that of the reactant side.
So it must have absorbed some energy.
Yep.
Internalized it, if you will. I don't need all the numbers personally, but I need the graphs to be right. The shape of the graph needs to be right. And then once we can do that, then we can get into labeling.
And it's only one way or the other. I better not see some crazy, weird potential energy diagrams on part two.
It's really that simple.
No, it either goes low and ends high, or starts high and ends low.
Yep.
That's it.
So now specifically here, these are the parts we need to label.
Mm-hmm.
So we're going to do them in definition piece first, then we're going to label. Right. So forward reaction again, left to right. Reactants to products.
Mm-hmm.
Right?
Yep.
And then
reverse reaction is right to left. So it's the backwards of the forward reaction. So we go from right to left.
Right.
Yeah, right to left, that way.
Right. Got those words mixed up.
You did?
Yeah. Oopsies.
No big deal.
But it goes back. It's got the reactants on the product side. That's all. That's why I get it now.
Yeah.
I get it.
Well, because if the reaction is reversed, what would typically be the product becomes the reactant.
Right.
So
exactly. Notice the arrow's the right way.
Right. You always point from reactant to the product.
Exactly.
It's just a question of which side is considered the reactants in a potential energy diagram, because both could be both.
Right. I just don't want us getting confused that he's right and we're right, but I just want to be confused.
I like being right. Yeah. The activated complex is a special scenario where all the atoms, molecules are breaking and forming their new bonds at the same time. This happens at the peak of the potential energy diagram.
So, and it's just this specific spot, and that's really all you need to know. We're not going to get into the craziness that is this weird chemical piece that doesn't show up on the product side or the reactant side, and only this happens instantaneously. You're never going to have to be able to predict what it physically is.
You can go
just
get
where it is.
You can go get your PhD studying activated complexes.
Seriously. The activation energy now is the energy to get me from the reactants up to the peak. Right. So I'm thinking about, I always like to think about a shopping cart, and I'm pushing that thing up this thing.
Yeah. How much energy does it take to get to the top of the hill so I can hop on and ride down the other side?
Right. Because once you get to the top, you can let go and the reaction will take off by itself. The car will go down the hill on the other side.
But if you don't get to the top, the reaction will never occur.
That's what I'm saying.
And so that's what activation energy and why it's important.
And so now catalysts come into play a little bit here.
They
provide this way to lower the height of that peak. That's that dotted line.
Mm-hmm.
Okay. And it makes it happen faster because I've essentially decreased that activation energy without being consumed.
It's also, catalysts are not only like tools that you use to get jobs done that aren't changed, but they're also a lot like tunnels through mountains. Highways and trains could go over the mountains, but a heck of a lot easier if you just went straight through it.
Right.
And so you still get from point A to point B. It's just you found an alternate pathway to get there.
That's really the definition. Overall heat of the reaction, we do this specifically by the heat of the reactants minus heat of the products, delta H. It's actually products
has to be, no, it's this reactants minus products, or is it backwards? You got it backwards again, Milks.
Cut and paste this work.
No, I didn't.
Anyways, it is products minus reactants. We need to fix that.
Yeah. Products minus reactants, and now that's not working. There we go. Reactants.
Fix it. Reactants. Right. It's products minus reactants. Always products minus reactants.
Always products.
Fix that. And then this helps us now. Positive number endo.
Negative number exo.
There we go.
Which match what you'll see on table I in the reference pack.
So you will at some point have to draw one of these from scratch.
Yep.
I would advise you do something very similar to what you're seeing right here.
Exactly.
So you draw your axes and then literally start low, go high.
Got to have a hill. If
You gotta have the hill.
because otherwise it's not really a potential energy diagram. I've seen some garbage ones in the past where kids do a flat line, and just connect the two with a straight line.
Ooh, no. That's
No.
more of a phase change diagram we were doing before.
Right. So don't get confused about all that business.
That
This is
hill
a
is
potential
important.
energy diagram.
That
The hill
hill is
is
important.
very important.
Now we can label up all these places. So this lower level is the potential energy, that's PE, of the reactants. Always start on the left-hand side.
Mhm.
Okay.
And the right-hand top of the hill is the potential energy of the products, what you made.
Right, and we've seen these in chemical reactions before. A plus a to B equals a C. So the A and the B is on the left here, the C is on the right.
Yep.
Okay, good.
Now, the amount of energy that is the difference, discounting the little hump over the hill, is the overall change in the heat of the reaction. That's our delta H.
Right now it's table I.
Table I, or heat of the products minus the heat of the reactant.
Right. There you go.
Okay.
Specifically, the little star up top. This is the noun. This is the activated complex, that very top of the hill,
Right.
which is good. And that gives me the total activation energy in the forward direction. How much energy it took to get to the top of the hill. One's a noun, one's a
From the
verb.
bottom of the hill on the left.
Yes.
Because there's an activation energy for the reverse reaction as well.
There is.
And it's
that's
right
this
there.
side.
It's less.
It is.
So the reverse reaction, again, coming from the left to the right, would be smaller hill to get over.
Right.
Now, a potential energy diagram for exothermic is going to have the same labels, but the only thing that's different
Is the potential energy of the reactants and the product switch,
that's it.
right?
So
So you're going
this
to
should
start
be quicker.
high and go low,
Still with a hump in the middle,
still with a hump in the middle, and
and
then we can start labeling it up.
so
Reactants are still on the left-hand side,
and the products are still on the right.
and the heat of the reaction is still just the difference.
Yep.
But now I'm going to have a different sign on my number.
Right.
If I do products minus reactants, I take a smaller number, subtract a bigger number, I get a negative.
And that's negative sign tells you that it's exothermic. Activated complex up at the tippity top of the roller coaster.
Yep. It's a noun. Leads us to a verb.
Activation energy of the forward reaction.
Forward, going from reactants towards products.
Exothermic reactions require very little bit of energy to get started,
Yep.
but they produce a lot of bit of energy on the other side.
Right. And then now the opposite is the reverse reaction. Would go from the products back to the reactants.
Because if you're trying to get this one to go in reverse, it would take a heck of a lot of energy just to get up to the top of the hill to roll down the hill on the other side.
Right. And then that is it.
That's all there is to it. So with potential energy diagrams, we got a lot of practicing, and it mostly comes down to your labeling. And
Yes.
some scenarios where the y-axis values for energy will make an appearance where you actually have to calculate delta H
Correct.
by doing the heat of the products minus the heat of the reactants.
And you
it's
can
just
get those from
subtraction.
these graphs.
If your graph is labeled up with a y-axis and good numbers to use, you can determine how much heat a reaction will produce.
Absolutely, just from the graph alone. Or the activation energy in the forward reaction.
Oh, I just got a great idea.
What's
Such
that?
a mean idea.
Go ahead.
Print out like 20 blank graphs and reference table I and say, set the scale on the y-axis and show me that this reaction is negative delta H or positive delta H. I had the idea. I didn't say I was going to do it. I want to.
Oh,
I think it would make them realize it, right?
I think they want this video to end.
Yes, they do.
So let's make that happen.
Bye.